Okay, so last time I gave you the formulas for area moment of inertias, moments of inertia, for simple shapes about their own neutral axis. And so now we have to do the parallel axis theorem for this. It's very similar to the parallel axis theorem for the mass moment of inertia. So if you have a two-dimensional cross-sectional shape like this, and say the centroid of this shape is here, then the neutral axis goes through the centroid like that. And say that you want to calculate the area moment of inertia about this axis A, okay? Then you have to figure out this vertical distance D, and the mass moment of inertia of this shape about A is equal, the area moment of inertia about this shape, sorry, is the area moment of inertia of that shape about its own neutral axis, plus the area times the distance squared. This is the area of the cross section. So one thing to notice about this, with the mass moment of inertia, about what point is the mass moment of inertia smallest?
The furthest point from the center of mass?
It's the opposite of what you're thinking. I mean, you're sort of thinking about it right. It's the center of mass is the smallest. And the biggest it could be is the, I mean, you could keep calculating it farther and farther away, so there's no limit to that. Well, it works the same with the area moment of inertia. The smallest area moment of inertia is the shape's neutral axis. Anything else gets bigger because you're just adding a positive number. So the smallest area moment of inertia is about the shape's neutral axis.
So I and A is what we calculate from the...
Yeah, this is from the formula, right? And then you're just going to add something to it given the distance. So let me show you an example of this. So let's do like a beam with a cross section of a T. It's probably called a T beam, but I don't know. Okay, so there's the beam. And so our coordinate system is going to look like this. Stop doing that. What axis is this for the beam? Yay, good work. And this, y. That wasn't as good. And then this is z. Okay, so we're going to calculate the area moment of inertia about the neutral axis of this cross section. And I'll give you the dimensions. So let's say that this distance is 0.5. Ooh, that's a big old beam. And the thickness everywhere is 1 centimeter. And this distance is 0.5 meters. And I'm going to break this up into the top rectangle 1 and the bottom rectangle 2. So the first thing I have to do is calculate the location of the centroid. So to start with, let's choose a coordinate system like this. So this would be the y-axis, this would be the z-axis. We're just doing this to find the location of the centroid. That's where we're going to reposition our coordinate system for the problem. Okay, so for rectangle 1, the area is 0.01 times 0.5, so 0.005.
Just a quick point, that's on the axis of symmetry?
Yeah, that's right. The centroid of rectangle 1 is 0 for x and 0.005 for y. And then for rectangle 2, the area is the same. And the centroid is 0 for x, negative 0.25 for y. A total is 0.01. And so the centroid is 1 over 0.01 times the quantity 0.005 times 0.005 plus 0.005 times the vector 0, negative 0.25. And I got a value of 0 for x, negative 0.124 for y. Anybody get that? No. 0.1225. Okay, I think that's right. All right, so now that we have this, we have to calculate, bless you, the area moment of inertia, the area moments of inertia of each of those two rectangles about this point. Okay, so what we calculated is that like this distance here is 0.1225. Okay. Okay, so for rectangle 1, the mass moment of inertia, the area moment of inertia, is 1/12. Rectangle 1 is the top one, times the base, which is small, 0.01, times, no.
We need the mass of each piece.
We don't need the mass because this is just area related.
Oh.
Okay. Yeah, doing this at the same time is like a mind twister. Okay, so the base is 0.5. The height is 1 centimeter, and that's cubed. And then we're taking that times the area of piece 1 times the distance squared from the centroid of piece 1 to the overall centroid. So that's going to be 0.005 to get from the centroid of the top rectangle down to the bottom of the top rectangle. And then another 0.1225 down. So that is 0.1275 squared. And if you multiply this out, you get 8.13 times 10 to the minus 5. And then for rectangle 2, you have 1/12. This rectangle is oriented the other way, so the base of this one is 1 centimeter. The height of this one is 0.5, and that's the one that's cubed. And then we're adding that to the area of that rectangle times okay, so in the original coordinate system, the centroid of this lower rectangle was 0.25 meters below the separation between those two rectangles. The centroid of the whole shape is only 0.1225 below. So we want to go 0.25 minus 0.1225. That's the distance we need to move this thing. So I guess because those two rectangles have the same shape, this distance is the same, 0.1275 squared. But you can just subtract to get that. And for this one, you get 18.53 times 10 to the minus 5. You can see the parallel axis theorem contribution is the same, but the contribution of the shape itself is way bigger for the one that's taller and not as wide. And so finally, the area moment of inertia of this shape about its neutral axis is the sum of those two, and it's 2.6 repeating times 10 to the minus 4 meters to the fourth. So let's do an example now. I'm going to give you a beam. And let's say the only loads on it are a compressive force of 1,500 newtons and a couple at this end of 200 Newton meters. And for the cross sections, we're going to first do this problem with this as a square cross section, and let's say that it has the same area as this one. Okay, so it's going to be, so the total area is 0.01. So we're first going to do this with this beam. And then we're going to do it with the beam that we just did in the last example. And what we're going to do is calculate the stresses. They're going to be the same everywhere, but let's calculate the stress tensor at a point let's say at the top of the cross section. Okay? So what's the process for this? We're going to calculate the internal loads. We're going to calculate the internal tension and the internal bending moment. And then we're going to use the formulas for those two things to calculate a stress tensor. And we'll see the difference between these two different cross sections. Well, first let's just do the internal loads calculation. That's going to be the same for both of them. We're ignoring the weight of this beam. We're assuming that's small compared to the external loads. Also, this has a length of 1 meter. Okay, so we have the 1500 Newton force and the 200 Newton meter couple. And that's going to be counteracted by a force this way, I'll call that R, and a couple this way, I'll call that MR. I'll use this as the about point for this external loads calculation. So Newton's second law, we're only worried about the x direction. So R minus 1500 is equal to 0. So R is positive 1500. And the moment equation about Z, we have MR minus 200 is equal to 0. So MR is equal to 200 Newton meters. And now we can do our cuts. How many cuts do we need? Just one, yep. So cut 1 is valid for x's all the way from 0 to 1. We have over here a force of 1500 and a couple of 200. And over here we have a tension and a bending moment. If you calculated shear force or torque, those would just both end up being 0. So Newton's second law in the x direction. Like, if you feel more comfortable, you can keep all that stuff in there, calculate all the components. You'll just get V is equal to 0 and torque is equal to 0. So 1500 plus T is equal to 0. So the internal tension is negative 1500. So is it in compression or tension?
Compression.
Yep, compression. And that makes sense with the way that force is applied. And then the moment equation, just about the z-axis, we have 200 plus m is equal to 0. So the bending moment is negative 200 Newton meters. And since this cut represents the whole beam, that's the internal tension and internal bending moment at everywhere inside the beam. Okay. Remember St. Venant's principle, like if somebody asked you to calculate the stress right at this endpoint, you'd want to be careful about that, you know, because if it's applied as a point force, there'd be weird deformations or whatever close to the end point. But once you get into the body of the thing, away from the two ends, these answers will be accurate. Okay, so let's do this first for the square cross section. Okay. So first, let's figure out the stress due to the tension. The XX stress is equal to negative 1500 divided by the cross-sectional area, which was 0.01. And so you get a value of negative 1.5 times 10 to the 5. And so the stress tensor due to tension is negative 1.5 times 10 to the 5. 0, 0, zeros everywhere. And let's do this at the top and the bottom. No, let's not, but I'll just calculate it at the end. But let's do it at the bottom instead of the top. Okay, and now we'll do, for the bending moment, our formula for the XX stress due to the bending moment is negative m times y over I. For that square cross section, I is just equal to 1/12 times the base times the height cubed.
If it's a point at the bottom, do we need to move?
For the area moment of inertia, it's always going to be the one about the cross-section centroid, about its neutral axis. But what's going to be different for the different points is that y. Okay, so if it was at the top, that y would be from the neutral axis up, so it would be positive 0.05. And at the bottom, it's going to be negative 0.05. All right, so this is 8.3 repeating times 10 to the minus 6 meters to the fourth. And so sigma xx is equal to negative, and then times the bending moment, which is negative 200. Times y, which is negative 0.05. That's from the middle of the square to the bottom. Divided by 8.3 repeating times 10 to the minus 6. Okay, so we have so negative 1.2 times 10 to the 6 pascals. So the stress tensor due to the bending moment is negative 1.2 times 10 to the 6, and then zeros everywhere else. And so the total stress tensor is the stress tensor due to the internal tension plus the stress tensor due to the bending moment. And that is, okay, so we add 1.5, so 0.15. So negative 1.35 times 10 to the 6, 0, 0, zeros everywhere. Okay? Yeah.
Will we ever, in a 2D, will we ever have to worry about a stress tensor because of the moment in any other direction other than X?
Moment is only in the X direction, but the torque and the shear force are gonna give shear stresses.
Yeah.
So we will see shear stresses, but these two things are just always going to be in X. And one thing I want you to notice is, so the reason I changed from I wrote the top at first and then changed to the bottom, is if we had used the top, that Y would have been positive, and our stress then would have come out positive. And so when we added those two stress tensors, we would have gotten those two stresses to sort of counteract each other. Do you see that? There's a compressive stress due to the compressive force on it. But at the top of the beam, there's a tensile stress, and those two are in opposite directions. Like you could actually get those two stresses to offset each other completely, even if you have like really big loads, you know? But so I chose the bottom where those two are gonna add, and we're gonna have the biggest problem, you know, if we're trying to figure out where this is gonna break. So if you're looking for a place where you're gonna have the biggest total tensile stress, or biggest total compressive stress, you want to look for the place where the tension and the bending moment are acting in the same direction, not where they're in opposite directions. Yeah?
Sorry, for the area moment of inertia, how do you determine what is the base and which is the height?
The base is along like Z, it's horizontal, and the height is, yeah.
Thank you.
And so, like, it makes sense if you think, okay, the one that's cubed in the formula is the one that, remember this example, like, in order for this to be the strongest, you want it like this, you want it really tall, and that's the one that you're cubing is the height. Yep. Okay, so now let's do the same thing for the area moment of inertia that we calculated in this example here, this T shape. Okay, so now we're going to the T shape cross section. Okay, so what do you expect to happen here? So we got a magnitude of 1.35 times 10 to the 6 pascals for a very, for a cross section where we weren't thinking that much about using our material efficiently, you know. So now with the T shape, we're using taking that same amount of material, and we're putting it into a shape that we're hoping is going to resist bending more because we're elongating it, getting that Y dimension, that height to be bigger. Okay. And so what you would expect to see is with those same loads applied, we're going to have a smaller, maximum stress for the T cross section. Does that make sense? Okay, so hopefully that's what we're gonna see. Well, we know that's what we're gonna see because everything is gonna, things are gonna change a little, but for the most part, you know, M is gonna stay the same, Y is gonna stay the same order of magnitude, but we're gonna divide by an area moment of inertia that's a lot bigger. And so that's gonna make the overall stress a lot smaller. Okay. Okay, well, first, the internal tension. The shape of the cross-section doesn't have any effect on that one. So the XX stress is negative 1,500 divided by the same cross-sectional area. It's the same amount of material. So that's still going to be negative 1.5 times 10 to the fifth. And so the stress tensor due to tension is negative 1.5 times 10 to the fifth, and zeros everywhere else. But the one that's going to be different is the bending moment. The XX stress is negative of the bending moment, which is negative 200, times, we're going to the bottom of this beam, so we have to go from, so we have to calculate the distance from the neutral axis of that triangular shape to the bottom. And, okay, so to get from, so look at this coordinate system over here. To get to the bottom of this T shape, you have to go down 0.5, okay? But to get to the neutral axis, you have to go down 0.1225. So our Y is going to be down 0.5 minus 0.1225. Are you with me on that reasoning? And so our Y, it's still going to be negative because we're going down, but this time it's negative 0.3775. And then we're dividing by the area moment of inertia for that T shape. So 2.6 repeating times 10 to the minus fourth. And this time we get a value of negative 2.83 times 10 to the fifth. Last time we got a value of negative 1.2 times 10 to the sixth. So this is a lot less stress due to bending, and we did that without changing the amount of material we had. We just changed the way it was oriented. Okay. So now the stress tensor due to bending is negative 2.83 times 10 to the fifth, 0, 0. And so the total stress tensor is the one for tension plus the one for bending moment. And that is negative 4.33 times 10 to the fifth 0, 0, and 0 is everywhere else. Okay. So this is the same amount of material as in part A. But it's a much smaller stress because of the more efficient cross-section. Yep.
So, just to clarify, y is always from the center of mass of the cross section to wherever you're trying to find the.
Yeah, that's right. And yeah, and don't call it the center of mass, call it the neutral axis. And it's where we put the origin of the coordinate system.
And then the second question, would this, I don't see why it wouldn't, but would this still work if like, let's say our T-beam was like sideways, so it's kind of like that?
Yeah, we can't do that because of the 4 requirements for this calculation of stress due to bending moment. Was it 4 or 3? I have to think about them, but it has to be straight, it has to be prismatic, and then it has to be, symmetric about the y-axis. So that's the one that it fails, yeah.
I had a question. So when you say like at a point at the top or bottom of the cross section, for the T shape, can you like pick a point on the T part of that shape or not?
Mm-hmm.
You can?
Yeah.
Okay.
Yep. So you would just you'd have to just calculate what the distance is from the neutral axis up to the top and plug that in.
Like in the X or the Z direction, would it be like fine if you were to like have it like off center? You know what I mean?
Yeah, so the way it works is for the bending moment, all that matters is the height. So anywhere horizontally along a line is the same stress. But we won't, that's how it'll be for shear force, for shear force too, but for torsion it'll be different. Where you are horizontally will matter for that one.
And then that covers the cross section. So then we'll have if we have all 4, we'll have a different answer for every point of the cross section.
That's right, yep. And so as we go, we're gonna get these new requirements to the point where there's only one specific type of beam where we could do every one of these calculations for.
Is it a rod?
It's funny. It's a hollow, like thin-walled rectangle. That's all we can do for everything. If you don't have torsion, then you have a lot more options. But torsion is the one that, like, we've already limited our options somewhat, and then torsion is going to limit it a ton. So, yeah. Any other questions? Okay, that's all.